All right, let's get started. Welcome to Lecture 11, Miscellaneous Topics. I'm not Professor Tesu Kim, as you all can tell. He's unfortunately not here. Instead, I will go through the topic and through the tutorial this week. He will be back next week. Some logistic things, nothing too exciting today. Still, the in-class CTF is going to be on December 1st. It's going to be a 24-hour CTF starting on Friday around 3:30 last for 24 hours, where you all submit your challenges by November 27th. Ideally earlier, because we also have to make sure that they run and are able to provide feedback. Lec11 is now out and due in a week from today. Sorry, in 6 days from today, on Thursday next week, just like all the other labs as well. And the Code Breaker Challenge, the NSA Code Breaker Challenge that you all probably already got started on, that is due December 8th, so even after the CTF. Lab 7 was due yesterday. Couple interesting challenges we had in that lab. One of them was a timing side channel password. That was the challenge where you could leak the password byte by byte. We'll have a graphic on that. A command injection attack, mini shell code, where you could inject a bash command into a server running through CGI parameters. We had Die Hard Stack Canary. Very interesting challenge. And for that, it's important to understand how fork works. That challenge was a little bit different. The 2048 game guessable. Time of check, time of use memo, that was a little bit also kind of related to what we do today, and then some other things like in our binary. Password. For this one, the password challenge, it goes through the password that you provide and checks whether it's the right password. And it does that by comparing each byte. So that way, by measuring the response time, you can easily see which byte is more likely, because if you got the right byte in that iteration, then it will also compare the next byte. And we even added a little sleep in there to make it a little bit easier. Still, the challenge is challenging. This is a challenge that you want to run definitely from the lab server, such to minimize the latency on the network, such as just within the server, to make it a little more stable. Maybe even do a couple of iterations for each byte to get a little more reliable data. Yeah. But this is how it looks like basically if you plot the response time. In this case, you already got the first byte, and then you wait for the second, or measure what it takes for the second one. And then you can easily see that one of them takes a bit longer to return. Die Hard, that was a little bit different, that challenge, because unlike all the other binaries, it had the server code in itself. So it had it opened the socket, bind the socket, listen on the socket, and accept connections on the socket. So all that would happen in the binary itself, and it also would fork in the binary. And that means the fork creates an almost perfect copy of the process. That means the canary doesn't change. It means in different connections, there is the same canary. So similar approach, we can guess the canary byte by byte. So instead of guessing 2 to the 64 or 56, we only we can brute force 8 times a byte. For today, we have a couple of other topics that are also very common. One of them is the integer overflow that can happen. A couple of interesting slides on that as well. Some web race condition, or how we can inject commands into when certain conditions are met. And overall, these 10 challenges in this lab have just interesting exploit techniques that didn't fit into one of the other categories that we have a full lab about. So integer representation. Integer representation is limited, so at some point, if we keep increasing an integer, at some point it will overlap. To understand what happens in the CPU is we need to look at how integers are represented in the registers that we work with, and that is a tooth complement, which you all, I'm sure, already heard about. Does anyone remember what the idea behind or the motivation for the tooth complement is? Yes.
If a to I has a value certainly larger than, I don't remember that value, but a to I stops at a certain value, so if you find a two's complement, at least for earlier apps, basically if there's too large in your teacher value, we used to use the two's complement in a to I.
Yes.
Has something to do with like saving the use of a bit, like for 0?
Mm-hmm. Yeah. So essentially, the idea is if we only have unsigned values, we don't need to do any kind of special representation. But this comes in when we have signed values. So the question is, how do we store negative values? And what we could do is just use one bit as to determine whether all the other, in the case of 32-bit, the other 31-bit represent use the one bit to represent whether it's a positive or negative number, and then everything else to indicate the value. But that leaves us with 2 zeros. And addition is also a bit counterintuitive, and implementing it in hardware also makes it a bit harder because we cannot do simple wraparounds going from one 0 to the other 0 because we have 2 zeros, for example. So instead what we do is we want to create that full wraparound such that from -1, when we increment 1, we get to 0. And that is essentially a shift by 1 of the negative numbers. So we end up having negative. The smallest value that we can represent is the absolute value is 1 higher than the maximum value of the signed integer that we can represent. That is the idea, and that leaves us that allows us to utilize the different instructions, add, sub, multiply on both the signed and unsigned integers, and also so we can just use those in both cases, but we still have the property of the most significant bit representing the signedness. So it's still 1 means negative and 0 means non-negative. So we don't lose that property. But also we only have one single 0, so there's a lot of advantages in representation. If you look at concrete numbers, how that will look like for 1 plus 2, nothing really changes. But if we have here, assuming we're in 32-bit, we have -1 that will be represented as all bits 1, and then we can add the 2, and then we just by adding these 2-bit values, we get an overflow of 1, and then by just adding these 2 here, we end up essentially with a bunch of zeros and 1, and the 1 in the front just gets cut off, and we have the one that we expect to have in this addition here. Same here if we add 2 negative numbers, so that automatically works with the same instructions that we use for unsigned values. The range, as we already talked about, for signed integers, we need to pay attention. There's one additional negative value that we can represent that we cannot represent in the positive, on the positive side. For unsigned integers, nothing really changes. You can use the full spectrum of 2 to the 32 values, including the 0. So if we go through, then so let's just say we have assembly code that adds up to two numbers. Let's say one of them is only f and one of them is fff and ends with a d. And we set these values and then we add them up, and there's a typo. We add them up, and then the question is we end up with fff. Okay, so there's a typo. Let's say we end up, yeah, this should be E here. Let's say we end up with D, and then the question is this actually -3 or is it a positive value? Can we distinguish between these two? Is there any way we can distinguish? No, there's no way we can distinguish just from looking at this code. Could be signed, could be unsigned. However, we might want to check in subsequent instructions whether there occurred an overflow, and whether an overflow occurred is different for signed and unsigned values that we add or that we do arithmetic with. So, for example, an overflow in unsigned values happens from the largest one to 0, and that is a different step from signed int max to signed int min, because that is suddenly at 80000, where we have that overflow to the smallest value. Therefore, we have two different bits in the flags register that distinguish between these two cases. We have the carry flag and we have the overflow flag. The overflow simply keeps track of signed overflows, and the carry flag of unsigned overflow. Yeah. So in this case, let's say we add up 1 and 2, which results in 3. No bits are set because no overflow happened, whether it's in signed or unsigned operation. If we look at this, we have FFFF, and we add up 2. So if we interpret that as a signed, that would be -1 plus 2, which ends up being 1. Which flags would be set? The overflow flag. Actually not, because the overflow would be in a signed case. It would be in an unsigned case, because in this case, -1 plus 2 ends up being 1. So if we treat these as signed, there did not happen any overflow. -1 plus 2 is 1. So if we treat these two as signed values, there's no overflow. If we treat these as unsigned values, so this one as unsigned int max plus 2, then we have an overflow to 1, because that value cannot represent it anymore. So we have an unsigned arithmetic overflow.
How does an instruction know if the variable is signed or unsigned?
It doesn't, and it doesn't have to, because if we interpret, if we go through this example, so if we assume that these two are signed, then there is no overflow. This is the correct result for the signed addition. So there is no signed overflow. But if we assume these two are unsigned, then this is not the correct result. So that's why it is an unsigned overflow. However, if we, then the fourth one would be the opposite. So this is the case where we have an overflow in the unsigned case, because going through 0 is okay for signed operations, but crossing 0 for the unsigned ones does not would cause an overflow. if we have these two values, this would be -1 and int min. So the smallest possible signed value. If we add up these two, in this case, we actually have both set. Because if we add these two up, this is the signed case that we have here. And this is never the correct result if I add up two negative numbers. So definitely it's a signed overflow, so overflow flag has to be set. But also if we interpret these as unsigned, there's no way we can represent this f only, which is the largest possible unsigned value. If we add anything to that, that has to be an unsigned overflow. So that's why both carry flag and overflow flag have to be set, have to be 1. The result, however, and this is also the case for the previous two, the most significant bit is still 0. And that's why the signed flag is not set.
Who's setting these flags?
The CPU for you. When the CPU does the addition instruction, it executes that, adds these two values, and sets the flags. And then subsequent instructions, for example, compare instruction, a jump instruction, a conditional jump instruction can use those flags to determine whether it should jump or not. We have one more case. This is the largest possible signed integer plus 1, and they will end up in the most significant bit being set. So the signed flag will be 1, and if we interpret that as a signed integer, it will be the smallest possible because the most significant bit is set. So it definitely has to be a signed overflow, because we add something to the largest possible signed value that cannot be represented as a signed, as correct in the range of the signed integers. But if we interpret these two as unsigned, then that is a legitimate operation. The highest signed integer plus 1 is still a legitimate unsigned integer. It's still in the range of unsigned integer. So carry flag is not set, overflow flag is set, and the signed flag is set because the most significant bit is set. Does that make sense? One thing to keep in mind with integer representation is it depends on the architecture you're compiling for. So while a character is always 1 byte and an unsigned character is also always 1 byte, at least in x86 and x86 64-bit, shorts and unsigned shorts are 2 bytes, integer are always 4 byte and unsigned. But long, it looks a little bit different. If we have a long on a 32-bit x86 machine or binary, that will be represented as 4 bytes, but not on a 64-bit. Same for pointers and size types. That's something to keep in mind. They are what they are compiled to is different and depends on the architecture. So what is with type conversion? We still want to do arithmetic with those variables, with numbers and variables, and that might require us to convert from one type to another type. From lower to higher precision, that should not be an issue. A character can be interpreted, the entire range of a signed character fits into a signed integer. And we can simply do that by sign extending the most significant bit, and then we end up in the same range. That is not a problem. In unsigned, that's also the case. That's also the same. We can simply zero extend. And we get from a char to an int. So for you, these two instructions move sign extended and move zero extended. For you or for a decompiler, that's an indicator for the type of the variable that is being moved. So that tells us or gives us a hint for whether the variable was signed or unsigned in the source program. From higher to lower precision, that becomes a little more challenging because we cannot represent the entire range in that smaller type. Architecturally, it's simple. We can just truncate what's in front, and we can do that, and that is basically a modulo operation. So from an integer to a character, there is a small. We truncate them to the range of the character, but we lose a lot of numbers and a lot of precision. And same for unsigned int. Here it's basically a modulo, and here we actually for the range of the character that is still correct, because we have that bit that is going to be indicating the sign in the character that will for the range that is being represented in integer, that will already be set, but not for other values. So let's do some example. We have three characters, C1, C2, C3, set to 103 and 4. And so the question is, what is the result going to be if we multiply two of them and then divide it by the fourth? So C1 by C2 is 300, which is larger than what can be represented in 1 byte. So what is the result in this case? Is it going to be 75, which is what we would expect in that mathematical operation, or is it going to be truncated and then set to 11? Because if we truncate the 300, which is hex 12c, cut off everything that is not in the least significant byte, so we get to the 2c, which is decimal 44 divided by 4, which would be 11. Any guesses? Any guesses?
Would it depend on the type of associated generated?
Correct. Then let me rephrase my question. What does the compiler generate?
I mean, since they're all static values, I'd say 2. I mean, I'd say 1.
So the one is actually correct. Since the compiler actually in this case does something that is called integer promotion, and it promotes before any arithmetic operations, all integer types that are smaller than the size of an int are promoted to int if the integer can represent the whole range of that type. So it promotes it to an integer, does the multiplication integer, and then casts it to the character, or converts it to a character to assign it to the variable. If that type could not be represented in integer, it is promoted to an unsigned int. This is this promotion of type in standard is meant to avoid overflows. However, it has turned out that actually is not the case and causes more harm than it solves problems. So this is something that it's very important to be aware of when we want to write secure software, and many people are not. So yeah, in our example, it gets promoted to integer and it results in 75. So let's do some examples and look at how the integer promotion works. So if we have a character and an unsigned character, and we add those to a long, by rule 1, we can character max, char max and unsigned char max. Those both fit into integer, and we can, and that's why we can. They get casted to integers and then assigned to a long, and we get the expected result. In this case, if we have -1 and 1, and want to make a compare those two, which is essentially just a subtraction, then in this case, they, however, since -1 is not, cannot, SI promotes to unsigned int. In this case, because in this operation, we have the two being promoted to integers, to unsigned integers, and it actually results up being 0. This is a little bit counterintuitive, but the reason is that the integer and the unsigned integer together, they don't cover the range of the integer. So overall, the range does not fit into a signed integer. So that's why they both get casted or promoted to an unsigned integer. So rule 2 applies, and it actually returns 0. Overflow of unsigned integers are well defined as wrapping. Overflow of signed integers are just by the standard undefined. That's just how it is. And however, they are well defined in the processor, at least in x86. So if we add up 1 to a signed integer, I will always, to the largest signed integer, I will always get the smallest possible signed integer. At least in x86, but that's not guaranteed by the C standard. Whereas for unsigned integers, it is guaranteed. Optimization takes a lot of advantage of this in library code, which makes it hard to understand. Or also in the compiler. So let's go through a couple of examples. 1 greater 0, both of them get casted to integer, and as expected, this is true, so we get 1 in x86. In this case, 1 greater than -1 casted to unsigned short. If you cast them to unsigned short, unsigned short can be unsigned short, not unsigned integer. Unsigned short, yes, that fits into integer, and so that means we can cast both to integer, and 1 greater 1 is correct, so we have 1, which is true. -1u, what does that u stand for? Unsigned integer, and 0. So in this case, the unsigned integer, it can't represent it as int because that is past the signed int. So everything gets promoted to unsigned integer, and in that case we have ff bis greater than 0, and that is true. So we actually get 1. -1 unsigned is greater than 0, which is not what we expect. This is critical for the tutorial. So if we have absolute of $2,147,000,000 something, or which is the equivalent of absolute of int minimum, in x86 32. Any guesses what that would be? Can we represent 2 billion? Can we represent, if we assume arbitrary precision, can we represent the 2 billion ending with 8 represent in a signed integer? No, we cannot, because that is one larger than the largest possible signed integer. So at the end of the day, if we look at the two's complement, what happens here is we negate so what the processor basically does is it negates the sign, meaning it sets this sign to 0 in this case, and then adds 1 to it, and then that will actually end up being the negative int min itself again. So in x86, where absolute would be, if we would implement absolute in longs on x86, then we would get the result. So if we would have longs here, integer is smaller 0. Now we're getting to a shift operation. Unsigned 1 shifted to the left by 0 positions, that just remains 1. If we left shift by 32, that is actually undefined in C, so the standard does not define what that outcome is. And on x86, that's typically 1. I tried it out. For me, it actually was 0. So it is truly undefined. So we can make sure what the outcome is. It will end up being a shift left instruction, shift left 32. Funnily, the left shift by negative number, that will shift it in the opposite direction, and that will actually wrap around. So shift right by 1 and wrap around, but that's again not defined. -1 left shifted by 2. That is because shift operations are only defined on unsigned integers. So undefined unsigned integers, that's why the result is undefined. However, we can still implement it in the processor doesn't care whether that's assigned or unsigned. So what it will do is we'll just shift the value of -1, which is only once, or only f in hex, by 2 to the left. So that means we get 2 0 bits on the least significant position, and that leaves us essentially with the -4. Int max +1. That's again undefined. So assuming we're talking about signed integers, then this is again undefined because that is an overflow in signed integers. On your 32-bit x86 processor, that will end up being setting only the most significant bit to 1, and everything else end up 0, because that's essentially 7FFF plus 1. And you can interpret that as signed or unsigned, whatever your program does. Unsigned int max +1, unsigned int max +1, that will result in 0. Since that's the largest unsigned value, if there's a wraparound, that is actually defined because it's unsigned, that will result in 0, and that's guaranteed. Negative int min, we already had that. That is undefined because it's assigned wraparound to the max, but it results in int min again. -1 greater than 1 on x86 and 64 on x86 32-bit. So if we look at this on a 64-bit machine, the size of long is actually 8 bytes. So that means the size of long is larger than the size of the unsigned int. So that fits into long. So both of them get promoted to long, and we can do the comparison, and we get the expected false. So that matches here. So the first one, this is 0. However, if we are on x86, then the long is a 4-byte value. So that means both of them have the same size, and that means they instead get promoted to unsigned int, because they both fit into unsigned int. And there, in unsigned int, we cannot do that. We cannot subtract. We cannot represent -1. It will be the largest possible value, and that is larger than 1, so it will result in 1. All right, that was all the examples for today. We're now going to go through the tutorial, which is 3 stages with different types of vulnerabilities that we'll go through. All right, any questions so far? Excellent. All right, I have a local environment here, which is equivalent to what's happening on the server. I am in the tutorial 08 logic bugs folder, and we have a crack me file, a readme, a snake, a target, and a template. So let's look at okay, the readme. Let's look at the crack me first. So if we go to the main function, the first thing it will do is call start asks for some password, some integer password, and then it will ask that the absolute value of that password is smaller than 0. Can you all see it, or is that too small? Okay, much more. Okay. So it asks whether that absolute value of the password is smaller than 0. Is that somehow possible? Can we, a positive, if we get an integer, turn it into an absolute value, that should always be at least 0 or greater than that. Do you have any idea how we can provide a value that turns the result of the absolute function into a negative value? Maybe let's look at the absolute function, and it literally just checks whether the provided integer is smaller than 0, and in that case it will return -I, or otherwise if it's positive it will just return the integer itself. Any idea? Yes?
Return the max negative?
Yes, that is a good idea. Maybe we can have a quick look at the target, which is the so let's have a look at absolute. Compare. Okay. And what it will do is literally just negate in that case. So if we provide the smallest negative, it should flip all the bits and increment 1, and then we should be back at the smallest possible value. let's have a look at whether that actually works. -2 to the 31. Let's provide that value. Okay, awesome. That's good. So that's the first stage, how we pass the absolute function. So then round 2, let's check what round 2 does here. It somehow generates a new password, saves the password into a vault, and we can look at what that is. Prints something, has a buffer, and then then calls scanf, so we can provide some value into that buffer, and it will call a to I on our buffer and compare that to the password that it previously generated. So let's see how the password is being generated. Okay, so we open def random. That is actually an indicator that the password is probably actually random. So we read from that file into some password integer, and then just sleep, print, and return that password. So the password is truly random. There's no way we can just guess that password. However, let's look at what happens in the save password into vault. So we get the password, that integer value, into that function, and it somehow writes it to a file that it opens, to a temp file. And temp file is just sitting in /temp.log and uses the PID of that current process. So it creates a log file, writes the password in there, and then closes the file, and then deletes the file again. Anyway, we can get the password from there. What are 2 things that we need to get the password from that file? Sorry?
We need to know process.
We need to know the PID. Yep. That's one thing. And the other thing? Or what do we have to watch out for when we try to read the file?
It's actually been created.
It always is being created. So it will always run through this code, so it will always create this file.
Sure, but we will still send it to our. I mean, we still have to perfectly time it, as in when we run our exploit. Has it been created?
Timing is the right word that I was looking for. So yeah, we need the right timing. We can just try and just open it, but and try to hit the right timing, but that's probably not going to work out. But we can see maybe it works. Let's try that. There is a template for this challenge. We provide a template in this case because the third stage will have some control characters in it, which make it a little bit harder to interact with through Pwn tools. So that's why this template exists. You can still solve this challenge with the Pwn tools if you prefer. So what we do here is we fork and then call execLE on the target. We do that such that we know the PID. It's very important to understand how the fork system call works. If you're not familiar with it, the man page of fork, I strongly recommend having a look at it and reading it. That will give you some insights, and we just use here a Python wrapper around that interface, around that system call, and it gives us the PID and a file descriptor to talk with the child. Yes?
Is this implementation of forks any different from the original?
No. It's just a wrapper around. It just makes the system call fork available in Python. Oh, okay, yeah.
Yeah.
Oh, you mean okay? No.
Is it different? No.
I think the API is slightly different.
Sure, but does the original fork also return the file description? I'm just curious.
I don't know off the top of my head. I would just have to look up the API online in the documentation. So in this case, we get the PID and the file descriptor to talk with that child process. So in the child, we just exec LE on the target, and in the parent, we can interact with that. So we can write something, and then we can .read. We can read, and then we can run this. Oh, okay. Actually, in Python 3, I'm not getting anything back. Let's do a. I'm not getting any idea why I'm not getting anything back. Should be able to get something back from the target. The reason here is that I just too quickly read returns without having before the target actually prints something to stand it out. So one way to solve this is just wrap this around. Like this, and then we should be able to get the output. All right. So it gives me the it gives me the prompt, but it does not say whether the password is right or wrong, which is because I'm missing a new line here. So it tells me invalid password, and then I'm getting an OS or input-output error because the target terminates and I'm trying to read or write to it, in this case. Yeah. So let's provide the value that we had here, which is this one. Let's provide this value here. And then we suddenly get to the point where we generate a password. And okay, so let's try. Let's try to get the password file. It's here. Pit, something like this, and then we should be able to read, and maybe we can just print it for now. Okay, so I get an error, file not found, no such file or directory, which was kind of expected, and even if I run again, chances are pretty low that I'll actually hit it in the right moment. So what we need to do is we need to wrap this around in a loop and just keep doing it, and then once we get it, we can break. But we also need to catch the exception in the case it fails, and then we should be able to get the password. Okay, let's see. All right, so it seems like it worked. It took a couple of seconds. That's what it takes for the target to print out that little animation. But we get a password. So it looks like this is what we need and what we just provide after the next prompt. So after we get the password, let's save that into a variable. And then let's write to the file descriptor the password that we just got. And then we should make it to the next stage. Let's see if that works. It's toString. Password which we got is not a byte string. Oh, I see. Let's just open this in. If you use the Python 2 on the lab server, you don't have that issue. Okay, seems like we missed the file creation in this case. Yeah, this can happen since it's a race condition that we're exploiting here. So that can happen that sometimes, even though we have that while true loop, sometimes we just don't hit the file. And sometimes we're unlucky, and that actually happens twice. Try open password file. Password. Password plus. Why are we not getting the password? Open password. Bytes as file descriptor. Read bytes. Oh, this is right. Password plus byte, new one. Let me check what I missed. Read password. Oh, okay. The problem here is on my side and not okay, here we go. I just forgot to convert that to a byte array. So looks good. We passed the first one, and now let's provide that password back again, and then we should be able to pass it the second time. And oh, okay, looks like the third stage is going on here, and this is basically a snake game. Okay, game over. But it seems like everything else worked out perfectly. So we exploited the integer overflow, and we exploited the race condition. And maybe let's see if we can find a third type of vulnerability in the snake game that we can exploit to get a shell. All right, let's close this. Yeah, this shell, this snake game is a retro game. It's just, I think, a single file. We actually provided in the in the snake folder. So this is Microsnake. This is a simple game. It's 20 years old, but still works. And based on curses or ncurses, which is a library to provide this nice little interface. So let's see what our target here calls after we pass round 2. It simply calls snake main. It's declared extern, so let's go to snake. And we see this is the entry to snake main. We actually don't need to understand the entire program here, but it's actually enough to look at what happens here right in the beginning. Can anyone spot any potential issue in these lines from where snake main starts to where my cursor is right now? There's not a lot of commands in there. Yes. Around STTY. So what is the problem? Correct. So the STTY here does not have an absolute path to the binary, to the executable that gets executed here. So what system will do is it will check in the path, environment, and variable and go through the paths in there and check whether one of those folders that are in the path environment variable contains an STTY binary and executes that once it finds it. What we can do, however, is we can actually control the environment. So we can set, which is what we've done before, set the path to, let's say, for example, something empty. And then let's see what happens. Oh, okay. STTY not found. So system tries to invoke a shell, which then tries to invoke STTY, and because we cleared the path, system can't find the STTY binary. So we can make use of that and actually set the path to a directory that we control, for example the current working directory, and then let's create a file STTY and just cat prog flag. Is that a good idea? Why do you think it's not a good idea? Correct, does not know where to find cats. So let's just give it an absolute path here. Okay, so we got STTY. In my case, STTY is already executable. Not CD. So I don't have to set it executable, but might have to do that. So let's run our exploit script again. Whew. Okay, awesome. We got a flag. So that's good. We can't really see the flag here right now. So what we can do is, if you look at how STTY here works, or how the snake checks the exit of the system is, it checks for the exit status, and it returns if it's not 0. So what we can do, just to make it a little bit nicer, is exit -1. And then it should not launch the snake program, but instead just print our flag. Awesome. Any questions regarding this tutorial or the slides? All right, let's quickly check README. So in this lab, there is a couple of different challenges: command injection, integer overflow, bug, race condition, some randomness, Django web server, a lot of different interesting things. Some of them are actually running on a port, like the web server where you want to interact with them. I in general recommend running everything from that server, since that just makes sure you don't have any network connectivity issues. It should work from outside too. If you all don't have any question for me today anymore, then that's it from my side, and I'm still here to answer any questions. Remember to work on that. Remember to work on the challenge as well for the CTF. Come up with an idea. If you have any questions, post. Feel free to post on at discussion. Do you already have the? You should have the instructions on the website for how to set up the challenge. Is that correct? Yes, it should already be on the website. I see someone. Okay. You probably do not have the sign up link yet where you can upload it, correct? Did you get that already? No. Okay, I'll provide that link where you can upload a archive file with your challenge.